Hello. Unique factorization in Z. This is a very short video. This should be very short, just a couple examples of this type of concept. Give the standard factorization for each of the following. So 50, 40, 5040, would be how you properly say it, but technically you can divide by 10. Obvious enough because of it being number looks like it. And 10 is 2 times 5, and 504 can be divided by 4, which is a good test because 500 can be divided by 4. I think is a very obvious thing. That's 4 more. You get 126, and then eventually that 126 can be broken down to 9 times 14. And this all gets broken down as follows. So you eventually get 2 to the 4th times 3 squared times 5 times 7. And that's your unique factorization, and then if you square the whole number, you just distribute the square. So you get 2 to the 4th power times 2. The 4th power times 2 is 2 to the 8th. 3 squared times, it raised to another power of 2 is 4 because 2 times 2, and then 5 and 7 gain a squared. And that's how it works. And then cubed, it's the same process. 3 times 4 is 12, 3 times 2 is 6, and 3 times 1 and 3 times 1 is 3. Basically, 5 and 7 respectively. List all the positive integral divisors of each of the following. 8. So 8 equals 2 cubed, and that means that A is equal, the set of them all, positive integral divisors, is equal to 1, 2, 4, 8, because that's 1, which is 2 to the 0 power, 2 to the 1st, 2 to the 2nd, and 2 to the 3rd power. And 16 is equal to 2 to the 4th power, so we can list all the positive integral divisors as set B equals 2 to the 0, 2 to 1, 2 squared, 2 cubed, 2 to the 4th power, which is 1, 2, 4, 8, 16. And 32, it's 2 to the 5th power, 64 is 2 to the 6th, and the same process plays out, for sets C and D respectively in these integral divisors. And that's just how you would understand a problem like that. Let A, B, and C be positive integers. How many positive integral divisors are there of 2 to the A power times 5b to the B power times 11 to the C power? So 2 to the A has A plus 1 positive integral divisors. Similarly, 5 to the B power has B plus 1 positive integral divisors, and 11 to the C power has C plus 1 positive integral divisors. Whatever those values of A, B, and C are, how to set up. The product is going to be the product of A plus 1, B plus 1, and C plus 1 for the number of positive integral divisors. They accumulate like that. That's just a fact. Think of when you're doing this. It's more of a simple logic problem, this one, because in any case, as you've seen before, the number of integral divisors is 1 more than the power. So 2 cubed has 4, 2 to the 4th. When its number just like that, it's 5, then 6 for 2 to the 5th, 7 for 2 to the 6th. Count them from up here. So really, it's always 1 more. And A, B, and C, any values they take on when you have this. You want to find out the number for 2 to the A times 5 to the B power times 11 to the C power. Well, the exact number of integral divisors will be the product A plus 1 times B plus 1 times C plus 1. And finally, how many pairs ST of positive integers satisfy both ST equals 55,440 and GCD ST equals 1? Okay, so this is pair. That means they must be distinct, which is something we'll talk about in a minute. So I factor down this one to its unique factorization. You can see the steps here. Just do divisions of the parts until you get to primes. So 2 to the 4th times 2 to the 4th times 3 squared times 5 times 7 times 11 is what this turns in. This can be factored into. And the standard factorization of repeatation. So the GCD, there's S and T equals 1. That means they share nothing in common besides division by 1. They're relatively prime. Do you remember? So that means that 2 divides t or 2 divides s, but not both. Same with 3, same with 5, same with 7, same with 11. So all of these can be divided once. They can be divided by each of these, but only one of them, but not both. So number of pairs of positive integers satisfying conditions is equal to 2 times 2 times 2 times 2 times 2 divided by 2, which is equal to 2 to the 4th. So there's 2 to the 4th power pairs, so if you really want to be that 2 to the 4th power is 16. So 16 pairs that satisfy this problem's condition of s times t equal 55,440 and GCD of st equals 1. That's pretty much how it's set up and solved, because you can only have one of these each. So 2, 2, 2, 2, and 2. You can have both, so you divide by 2 in the end. These are distinct. You have 5 pairs possible, so multiply them together and you divide by 2 in the end. You get 2 to the 4th.